Hello, we are Group 3. What we are going to present today is about porphyry copper. Our member Saraku, Donggu Lee, Bhavin Patel. I am Dongku Lee. First slide describes this mineral features briefly. Porphyry copper deposit consists of disseminated copper minerals and copper minerals in veins and breccias. They are distributed in large volumes of rock, forming high tonnage, low to moderate grade ores. Host rocks are altered related to intrusions and adjacent wall rocks. For commodities, porphyry copper deposits are mined primarily for copper, and molybdenum and gold are co-products in some deposits, and with the silver a byproduct in many deposits. For ore minerals, although substantial amount of copper may occur as a bonite, energite, and chalcocite. In hypozine part of porphyry copper deposit, the copper occurs predominantly in chalcopyrite. Byproduct minerals frequently include molybdenite and native gold. Other associated minerals may include sphalerite and galena, tetrahedrite, and gold telluride. The porphyry copper is formed in tectonic plate convergence zones where oceanic crust has subducted beneath the continental crust. As the plate subducts, overlying upper mantle partially melt, and the liquid magma rise to the surface by flowing through cracks and fissures. Metals precipitate out of the solution as fluid cools and moves away from the heat source.
So I'm just going to go through the next few slides, starting with the global distribution. So porphyry copper deposits are distributed based on the tectonic setting. Almost all are found in magmatic arcs associated with subduction zones, with preference to regions that have thick arc crusts such as continental arcs and mature island arcs, and they're commonly located around the Circum-Pacific. There are a few large mines that are found in British Columbia, Arizona, Chile, and Peru. As you can see on the map, predominantly the deposits are Mesozoic or Cenozoic in age. Alteration in ore mineralization occurs between 1 and 4 kilometers depth above a cooling magma reservoir that can be located in a low crust like 6 to 8 kilometers. Porphyry copper deposits are associated with shallow intermediate complexes, and they form as a result of fluids derived from crystallized magma or reservoirs. Some fluids can even come from reservoirs that are 8 to 20 kilometers deep, and they're intermediate in composition in the magmatic arc environments. The image shows the location of the porphyry copper deposit in a volcanic zone, and steam occurs at about 600 degrees Celsius, and then the minerals are deposited between 350 and 250 degrees Celsius. Porphyry copper mineralization and alteration occurs in variable rock types, but is commonly hosted in volcanic, intrusive igneous, and sedimentary. carbonate are the most common type of sedimentary units, and igneous rocks associated are felsic to intermediate, calc alkaline, granodioritic derived from mantle magma, mafic or dioritic in island arc settings, and alkaline in back arc settings. The image shows a cross-section of a porphyry copper system with alteration assemblages occurring in sedimentary limestone, sandstone, and volcanic rock with a porphyry intrusion. Formation of porphyry copper requires a source of metal, transportation mechanism, and trap or deposition. These deposits follow a magmatic hydrothermal model. Magma which contains the metal rises, and as it reaches the surface it cools, and high-pressure steam is released containing copper, silver, and molybdenum. This steam is transported into the cracks in host rocks. As the steam condenses, the metals are transported in the veins and channels. Copper and molybdenum get deposited first, and then lead and zinc. As a result of the formation process, the copper deposit alteration zone is usually shaped as a semi-spherical or elliptical plan view. The dimensions of the porphyry copper, including the alteration ore bodies and sulfide-bearing rock, are found to be 4 to 5 kilometers long, with a median area of 7 to 8 kilometers squared. The deposit is usually surrounded by a hydrothermal alteration zone, including a potassic, phyllic, and propylitic zone. As the hydrothermal fluids travel away from the center, it alters the rock. High pressure and temperature closer to the intrusion result in potassic alteration, and propylitic alteration occurs farther from the center in low temperature and pressure areas. Ore is deposited between the potassic and phyllic alteration zones. There is a pyrite halo around the ore. Chlorite and calcite are commonly present in the propylitic alteration, and pyrite is commonly found in the phyllic alteration. And K-feldspar and biotite are found in the potassic alteration zone. Minerals may be disseminated in the host rock. These are fine-grained ore minerals scattered throughout the host rock, and there may be veins, breccia, specifically stockwork veining, which is a dense irregular network of fractures and veins that commonly contain minor amounts of mineralization. The figure on the left is chalcopyrite and bornite-rich quartz apatite veins and veinlets cutting biotite and porphyry. This is a high-grade ore, and this deposit was found in British Columbia. The figure on the right is quartz molybdenite and stockwork veining in grand diorite porphyry, and this was also found in British Columbia.
Hi, my name is Bhavin Patel and I am going to continue the presentation with deposit examples. For that, Chile is the world's leading copper producer, which is accounting for 5% of the total world's copper output and is the hotspot for copper porphyry as well. The Escondida mining complex in Chile has the world's largest copper deposit and produces 1 million metric ton of copper per year from two supergene enriched copper molybdenum porphyries. Colhousy mine, which is towards north of the Escondida mine and second largest deposit, producing 559,000 metric tons of copper. Bingham mine is located in Utah and which is the deepest open pit mine in the world since 1906. It has produced 300,000 tons of copper, 400,000 ounces of gold, and 4 million ounces of silver and 30 million pounds of molybdenum. If we talk about grades and tonnage, higher the grade of mineral deposit, more economically it is, as it is cheaper to extract. But for copper porphyry deposit, there is an exception of low grade mining. Grade of copper in copper porphyry deposit range from 0.2% to more than 1%. that is around 1,800 grams per ton to more than 9,000 grams per ton, with other elements like molybdenum ranging from approximately 0.005% to 0.03%. Gold is ranging from 0.004 grams per ton to 0.35 grams per ton, and silver is ranging from 0.2 grams per ton to 5 grams per ton. If we talk about mineral exploration techniques, for exploration of porphyry copper deposits, modern geophysical methods are useful in the most of the cases. Techniques like aeromagnetic, seismic, gravity, and remote sensing aid in getting information of broad crustal structure and magmatic setting of mineralized zones. Minerals of diverse geophysical properties are concentrated near the topographic surface in porphyry copper deposits. Like magnetite, distribution ranges from abundant to non-existent depending on the type of intensity of alteration mineralization and parent lithology of porphyry copper deposits. This porphyry copper associated alteration occurs in the zone which causes predictable special patterns of magnetic anomalies which can be mapped by high resolution airborne and ground based magnetic surveys. Sulfides of iron and copper are distributed throughout most of the alteration zones. To detect them, electrical and electromagnetic methods are used as these minerals have low resistivity. These surveys are usually combined with induced polarization technique, which is used to show chargeability, that is, the availability to reversibly store electric charges at the low frequency of crustal material. Induced polarization surveys were initially found for the exploration of porphyry copper deposit and hence are the widely used for the same. Three-dimensional framework of porphyry copper deposit can be indicated with the help of sophisticated inverse methods that are applied to electric and electromagnetic data. Lithography that surrounds porphyry copper deposits are identified using seismic velocity, which is provided by seismic reflection and seismic tomographic methods. Geochemical methods like soil geochemical surveys have been useful for exploration of porphyry copper deposits. However, the data must take glaciation and its effect into the account, which complicates the result because of incomplete understanding of glaciation. Geology is never simple though, hence geological mapping techniques should be used to support geophysical methods. To summarize the presentation, porphyry copper has spread out copper minerals throughout the rock bodies which surrounds the igneous intrusions. Primary product is a copper, while molybdenum, gold, silver are byproducts. Sulfide minerals, chalcopyrite is the principal ore minerals. Forms in convergence zones and found most commonly in circum-Pacific, Chile being the a hotspot. Follows magmatic hydrothermal model in the process of formation and forms semi-spherical or elliptical deposits. Can be hosted in fractures, vein and breccias. Low copper grades of 0.2% to more than 1%. Geophysical along with geological techniques are most useful for mineral exploration.